Displaying.
You're
All right.
good.
Thank you very much. Well, welcome all of you, and thank you for joining us today for another event of Webinar Wednesday here at Varitec, hosted by Varitec's Technical Institute. Today we're doing session 2 in the fundamentals of HVAC, and we're going to approach the topic of humidity. What is humidity, and why is humidity important to create better indoor air quality, and even, since we've learned from the pandemic, reduces the risk of infection within a building. My name is Dan Hahne of Varitec, Director of High Performance HVAC Solutions. Varitec is historically known as a manufacturer's rep organization, a manufacturer's rep firm. However, we have recently developed over the last few years into really an integrated HVAC system solution provider. I won't go into my introductions. Many of you are joining us from previous sessions. Any personal information will be available on the PDF Kelly will be uploading to our training website, so you can access that information if you should have any need for it. So again, I don't think there's any further addition for introductions to Varitec, our capabilities, our controlled solutions for innovative HVAC designs, and our staying on top of the developing trends within our market today, and that might be influencing how HVAC systems are laid out and designed to attain certain indoor air conditions that are conducive to thermal comfort and better human health. Just wanted to touch base on our future webinar sessions, and I want to offer you an early invitation on May 10th to session 3 of the fundamentals of HVAC. We're going to approach psychrometrics. The title of the presentation is Psychrometrics Deconstructed. We will make sure we understand all the fundamental terms involved in the states of air, the properties of air, dry bulb, wet bulb, specific humidity, etc. Review all of those terms and their meanings in detail, and then deconstruct the psychrometric chart and rebuild it, so hopefully we will be able to more effectively understand how we can use and apply the chart as a reference sheet to calculate air conditions, states of air, and properties of air, both for future designs and existing conditions. Webinar Wednesday is currently on board to continue through to November 8th, so stay tuned, and we would welcome your input on future topics they would like to have us cover and present on these Wednesday monthly events. Be aware of Varitec's monthly newsletter. The April edition was released a day or two ago. The newsletter is specifically to keep our client base informed of what are the developing trends nationally and globally within the built environment, why those trends are occurring, perhaps the science behind them, and so that you can be better prepared and informed of how building designs are going to be shaped in the future. April's edition celebrates Earth Month or Earth Day, and consequently we have some material on that newsletter that regarding carbon neutrality, the influence of carbon on global on climate change, and also we have one HVAC solution that will help us increase the efficiency of building designs, as well as creating better IAQ during our part load conditions. So stay tuned. Let us move on, because we got quite a bit of material to cover. And as I've said in the past, that these presentations are somewhat dense with information, so they can be used afterward as a resource. If you have any questions, if you want to use it as a reference platform for questions you may have in the future, hopefully we've got an expansive bit of information within this deck that might be able to answer a number of your questions in the future. Today, however, we're going to do a quick review of session 1, HVAC fundamentals. We're going to make sure we understand the terms used and how they move into today's session on humidity. We're going to explore the nature of water, the states of water, terms and definitions associated with water, especially in a vapor state, and the physics of water vapor, how water vapor moves from high humidity states to low humidity states, and what drives that direction. Then we're going to look at ASHRAE's position document on infectious aerosols and explore why humidity, properly controlled humidity in a building, not only adds to better human health, but it also reduces the risk of infection in a space that we'll examine more closely as well. And then offer one quick solution that is available today in the market to help us regain some of the moisture that would otherwise be exhausted from the space or condensed out of the cooling coil, so we can maintain humidity levels at a healthier level during our dry fall, winter, and spring months. So let's begin. Let's look at a review of the last presentation. Again, I introduced you to ASHRAE, the American Society of Heating and Refrigeration and Air Conditioning Engineers. It's an association that really writes the heating and ventilating standards for buildings. They define thermal comfort conditions through Standard 55. They determine ventilation rates within a building to provide better IAQ. They write the standards for healthcare facilities, as mentioned, as stated in ASHRAE Standard 170. Again, ASHRAE's mission statement and our continuing resource is to serve humanity by advancing the arts and sciences of heating, ventilation, air conditioning, refrigeration, and their allied fields. In the last session, we looked at thermal comfort, and we brought forward ASHRAE Standard 55's somewhat scientific definition of thermal comfort as being the condition of mind that expresses satisfaction with the thermal environment and is assessed by subjective evaluation. I think we mentioned at that time that a building is properly designed if 80% of the occupants in the building are satisfied. You can never provide a design that provides 100% satisfaction for all the occupants for reasons we covered in last month's session. Also, HVAC is to create better indoor air quality by maintaining proper ventilation rates, bringing in assigned minimum amounts of outside air to allow us to maintain a healthier environment. We also explored ASHRAE Standard 55 and the various factors that contribute to thermal comfort. We looked at temperature, humidity, radiant heat, airspeed, occupant metabolic rate, and clothing insulation. 6 factors that affect an occupant's sense of being comfortable. And we explored those in detail. A couple of the items that we're going to cover today, though, in our review do apply to the humidity question that we're going to be covering in greater detail shortly. First of all, let's look at temperature. The definition of temperature is a measure of the amount of thermal energy in the air. What is the rate of molecular motion in the air? The higher the molecular motion, the more energy, the more thermal energy, and the greater heat is sensed in that environment. Reduced molecular activity in the space suggests an absence of thermal energy and consequently a cool environment. The amount of energy present in that sample of air is measured in British thermal units, BTUs. 1 BTU is the amount of energy to raise 1 pound of water 1 degree Fahrenheit, and 1 ton of energy load is equal to 12,000 BTUs of energy. So what does that mean? A 4-ton package DX unit has, at ideal conditions, a capacity of 48,000 BTUs, or 4 tons. So that's how you can apply and equate BTUs to tonnage. Remember that thermal energy is sensible heat energy, and this is going to come back again in the next presentation on psychrometrics deconstructed. So stay tuned for that. So temperature is a measure of the amount of thermal energy within a space. We looked at factor 2, humidity, and we identified the relationship between thermal energy and water. So The state of water, we mentioned as well, is determined by how much energy is present in a sample of water. The higher the fluid temperature, the greater molecular activity within that fluid, just as in air with thermal energy. And the greater the molecular activity of water is the greater evaporation rate. Water breaks free of its fluid state and becomes a vapor. And we're going to explore that. The energy required to keep water in a vapor state as a gas is referenced as latent energy. Why latent? Well, we can't perceive it. If there's high humidity, we can feel humidity. That is to say, we can feel dampness. But we don't feel the energy that keeps water in a vapor state, which when removed, water can no longer sustain itself as a gas and becomes a liquid, otherwise known as the process of condensation. There's something about water vapor, however, that we're going to touch on over and over again, that a wet condition always moves to a dry condition. We also covered heat transfer. We looked at the purpose and modes of heat transfer. Energy, like moisture, moves from high energy states to low energy states. That's just the natural order of heat transfer. HVAC systems in cooling, the fundamental purpose of a HVAC system is to move energy. We can maintain thermal comfort by removing the amount of energy gained in a building during our hotter times of the years and during occupied hours, or we have to add energy when we're in heating mode, when it's so cold outside that the ambient condition robs the energy heat gain from the building. Consequently, we have to supplement thermal energy in heating mode. There are 4 modes of heat transfer in the domain of physics. They are conduction, convection, radiation, and evaporation. No more, no less. And we explored each of those modes of heat transfer in the previous session. So if we're going to be moving energy through an HVAC system, we have to have a heat transfer medium, something that is able to carry heat from one location to another, from inside a building to outside a building. So a heat transfer fluid is a gas or liquid that takes part in heat transfer by serving as an intermediary in cooling on one side of a process, transporting it and storing thermal energy and heating on another side of the process. We examined how there were 3 heat transfer mediums available: air, water, and refrigerant, and we demonstrated that the primary heat transfer for a building in a conventional HVAC system is air. We push a lot of air through a building to capture the energy gain in that building and to bring it back to a cooling coil where it's removed and consequently either through a condenser or a central plant deposited to outdoors. So with that being said, in that quick review, let us look at today's main topic, humidification. What is water? What is the nature of water? If you don't mind, I'm going to beg your indulgence. We're going to explore a few fundamental terms. We're going to go back to high school physics to make sure we have a common understanding of the terms so that when we use them, we understand how they're being used. We're going to look at energy, equilibrium, force, and pressure right out of high school physics class. And then we're going to look at the states of water. We're going to look at relative humidity, vapor pressure, dew point, specific humidity, and absolute humidity. So first of all, let us again review what energy is, because that is the fundamental purpose of an HVAC system, is to move energy. Energy in physics is the capacity for doing work. All forms of energy are associated with motion. So energy is the physical cause or force of motion and quantitative or qualitative states, change. So what is change? Well, it's to make something different. It's to alter something. For HVAC, change means to create a change of state, to create and move energy from one state to another state. In order to do that, we have to use force. So what is the definition of force? It is any action that tends to maintain or alter the motion of a body or to distort it. You may ask, what does this have to do with humidity? Hopefully, I will demonstrate that in just a few moments. In language that, or in the HVAC language, we use force to move the energy. We need some sort of force to move energy in a stable state and to move it to another location. What is pressure? Well, pressure is a physical force that when exerted on or against an object or something in contact with it, we bring about change. So thermal energy and heat transfer. First of all, we have heat transfer occurring naturally all the time. Wherever there's an imbalance of energy, we have a high energy state moving to a low energy state, because in the domain of physics, wherever there's an energy imbalance, there's a movement towards equilibrium. The whole universe is moving towards equilibrium, otherwise known as a state of entropy. Heat energy always moves to cold, and it does so by conduction, convection, and radiation. Also evaporation, but we're not going to be discussing that today. Pressure. Differences in states of pressure also result in movement or change. Air or moisture at high pressure states will always tend to lower pressure states in conformance to the physical laws of equilibrium. So, what does that have to do with water vapor? Well, like thermal energy, moisture will always move from wet conditions to drier conditions to achieve a state of hydrous equilibrium, complete balance of distribution of moisture content in a vapor state. That movement occurs by a principle called vapor pressure. Well, before we look at what vapor pressure is, let's examine water and its state, and its three states. Water can exist as a liquid, gas, or a solid. What determines the state of water is the amount of energy present to a sample of water. If you add enough energy to water liquid, it will become a gas or water vapor. If you remove enough energy from water liquid, it will freeze and become a solid. Or if you remove enough energy from water as a gas or water vapor, it will become a liquid again. So humidity control involves energy control. So what is relative humidity? Relative humidity is a measure of water in the air in respect to the amount of water air can hold at a given temperature. And when air is 100% saturated, when at a given temperature, it can no longer hold any more water, then that state is called saturation state. Now remember, look at the chart or the graphics to the right. And let's look at relative humidity. Why is relative humidity relative? Because its value is relative to the temperature of a sample of water vapor. Let's look at water vapor to a sample of air that is at 100% relative humidity. At 50 degrees Fahrenheit, 100% humidity, you have a given dew point. That is the absolute measurement of the amount of water in the air. If we raise that temperature from 50 degrees to 68 degrees, we now have 52% relative humidity. If we raise it even further, we now have 28% relative humidity. However, if we look at absolute metrics for determining water content in a sample of air, we notice that under all three different temperatures and relative humidity conditions, the dew point of the sample of air is always the same, approximately 49 degrees. The specific humidity is always the same, 51.91 degrees. And the vapor pressure remains the same because vapor pressure is associated with absolute moisture content. Because of the relative nature of relative humidity, ASHRAE standard 62.1 2019 has moved away from relative humidity as a design standard and moving towards dew point. And that's a good move because dew point conditions are not impacted by temperature. So what force drives water vapor from wet environments to dry environments? Vapor pressure. The natural force is the natural force that drives water vapor from wetter environments to drier environments to create a state of equilibrium. So what is vapor pressure? It is the pressure of the vapor resulting from evaporation of a liquid above a sample of liquid. That's the absolute definition. So the vapor pressure of a liquid, however, varies with its temperature. You have higher evaporation rates of water at a higher temperature than, of course, at a lower temperature rate. So what brings about a phase change? Adding thermal energy to a liquid will create and facilitate a phase change from water liquid into a water vapor. Let's look at dew point. What is dew point? Dew point is the temperature a sample of air must be cooled to achieve saturation, 100% relative humidity, where that sample of air can hold no more water vapor. It is the condensing temperature. It is the temperature at which there is not enough energy in a sample of water vapor that to maintain the water vapor in a vapor state, and it condenses into a liquid. That is the dew point temperature. So dew point is a measure of the actual moisture content in the air, and if you have a sample of air with a given moisture content, the dew point will be the same whether or not that sample of air is 50 degrees, 68 degrees, 86 degrees, or 115 degrees. So again, be aware that ASHRAE standard 62.1 2019 has made the move to dew point as the basis for moisture content in future building design recommendations. Let's look at the term specific humidity. What is specific humidity? It is a measure of the actual amount of water vapor in a sample of air regardless of temperature. It is a value that represents the absolute amount of water in that sample of air as measured in grains. There are 7,000 grains of moisture in 1 pound of water. And a grain of water has a weight of approximately 0.002 ounces. So understanding psychrometrics and knowing what specific humidity is, you can calculate the volume or the mass of water in a sample of air. And if you can calculate the mass of water in the sample of air, you can also count the weight of water in the air. A topic that is becoming more and more popular with architects and owners who are looking for more sustainable building designs that reduce water consumption because they want to calculate how much water can be removed from a building's air in order to be used as gray water for landscaping purposes and etc. So this is an important value that will be gaining more and more attention in the future. So with these few principles of water, let's go ahead and look at how water vapor behaves. And we're going to use an example of Dan's office. As an interest, I do a lot of photography, and I decided years ago that I was unhappy with some other third party doing the prints of the images that I've taken. So I decided to get involved in doing my own printing. I use archival grade paper, and to maintain the life of the paper and hopefully photographs, we'll find out over the years, I need to maintain my room condition roughly at 75 degrees dry bulb, 40% RH. If you look at the psychrometrics of that air sample condition at 75, 40% RH, that sample of air has a dew point at 49 degrees, meaning that if there's a surface temperature in my office at 49 degrees, there is not enough energy present in the air adjacent to that surface to keep it in a vapor state, and it condenses. For example, a glass of iced tea on my desk. Condensation will occur on that glass if it is 49 degrees or less. The specific humidity of the room is 53.9 grains per pound of air, and the vapor pressure is positive at 0.35 inches of mercury. So one January morning, I was in my office. I usually work very early in the mornings on the photography. And outside it was about 45 degrees. Well, it was 45 degrees, at least according to the Weather Service, with a relative humidity of 92% RH. And I thought, well, in order to keep my space at 40% RH, I don't need to put my room humidifier on. It's raining outside. There's a lot of outdoor moisture outside. So I ran a calculation of the absolute conditions of the air outside and discovered that the dew point was at 42.83 degrees, which makes sense. It's raining. It's 45 degrees outside generally. Okay, that makes sense. The specific humidity is 42.44 for grains of moisture per pound of air outdoors, and the vapor pressure outdoor was 0.27. So I ran the calculations for my studio thinking, we've got a lot of moisture coming into my office because I'm only at 40% RH. Well, if we look at the conditions of the office, again, dew point was 49 at 40% RH. Specific humidity is 53.91 and vapor pressure is 0.35. The vapor pressure of my office was greater than outdoors. So consequently, my little office was trying to humidify all of Maricopa County when it was raining outside. So vapor pressure and knowing what vapor pressure is will help us understand the direction of moisture flow from high humidity states to low humidity states. And I know this is counterintuitive. For God's sake, it's raining outside. But it is drier outside under those conditions to an indoor environment of equal design conditions as my office. So I just started playing with the numbers using psychrometrics, and I thought, well, let's evaluate our wettest time of year. Let's look at our Arizona, our Phoenix monsoon design day. On a monsoon design day, many engineers use a value of 97 degrees dry bulb and 78 degrees wet bulb. It varies. Some engineers use 97 degrees dry bulb, 76 degrees wet bulb. I thought we would use 78 degrees because we're seeing dew points now on an August morning. I've measured them myself at 72 degrees, which means that at 72 degrees and below, water vapor will become water liquid. You'll have condensation. So if we look at the absolute conditions of this condition of outdoor air during monsoon, we have dew point at 71.31 degrees, a specific humidity of 120.82 grains of moisture per pound of air, and look at the vapor pressure, 0.773. It's double the vapor pressure of my office. Consequently, during a monsoon design day of these conditions, there's a lot of moisture in the air outdoors racing into my office. I don't have to turn my humidifier on at all. So that's good. So I thought, well, let's explore this a little more. Obviously, I should probably run my humidifier during Arizona summer dry day design conditions. So we look at an Arizona summer design day of June, roughly 115. Not uncommon to see 15% relative humidity. If we look at the states of air under 115, 50% RH, we look at these absolute values of water content. Dew point is 55.9 degrees. Specific humidity is 55.9 grains per pound of air. And vapor pressure is 0.45 inches of mercury. There's more grains of moisture in a sample of air at 115, 15% RH, than there is in my office, which means I don't have a dry building to worry about. If anything, I need to dehumidify the building. There's moisture outdoors at 115 trying to get into my space under the conditions of 75-40% RH. So what does this tell you? This tells you that our driest time of the year is not dry summer, June, early July. It is our coldest times of year. It is November, December, January. This is when we experience our ultra dry conditions, not in Phoenix when it's 115. So what does that mean with regard to enthalpy, a term that I covered previously? What is enthalpy? Enthalpy is the total load. The enthalpy or total energy of a sample of air is made up of the sensible heat energy plus the latent energy, the energy to sustain water in a vapor state. So let's look at Arizona on a 115-degree design day at 15% RH. The total amount of energy in a sample of air is 38.69 BTUs per 1 pound of air. Compare that to the monsoon day, where we have higher humidity. Enthalpy is 42.36. Our peak summer design condition is summer Phoenix monsoon at 97 degrees 78 versus 115 and 15% RH. And this is an important understanding to have if you certainly are intending on controlling humidity within a building. Well, congratulations. You've graduated Psychrometrics 101 in evaluating some of the fundamental properties of air. And again, if I'd like to invite you early to join us in our May webinar Wednesday on Psychrometrics Deconstructed, where we actually pull apart the spaghetti of a reference chart called the psychrometric chart as devised by Willis Carrier, and try to make some sense of it so we can apply it most effectively as and when we may need to. So, what is the relationship between humidity and condensation in building? And why is it important to maintain humidity and control humidity levels in a building? So let's look at a building. When does condensation occur? When we lose room dew point control. And this is very important to understand. When we lose room dew point control, whenever a room wall, window, wall register temperature is equal to the room dew point, that surface will condense water vapor into liquid. So let's look at a room design condition as advocated by ASHRAE Standard 55 of 75 degrees dry bulb at 50% relative humidity, equaling a room dew point condition of 55 degrees and a vapor pressure of 0.438. Again, let us remember, wherever there's an imbalance of moisture or water vapor, and wherever we see a differential in vapor pressure, a condition at high vapor pressure always moves moisture to a condition of low vapor pressure. So as we demonstrated on our monsoon and even our dry summer design conditions, water vapor outdoors is always trying to and will succeed getting indoors unless you have vapor barriers in the perimeters of buildings. So be aware of that. There's no way you can stop that unless you do put vapor barriers in a building. So let's look at a monsoon design condition. Let's look at an outdoor condition in 97-78. We've seen the radical differential in vapor pressure and the force that's pushing moisture from outdoors into a building that we're trying to control to 50% RH and a 55-degree dew point. So let's look at our conventional Phoenix design condition. Many times we see air handlers laid out to provide 55-degree dry bulb, 54-degree wet bulb off of a cooling coil of an air handler. That condition equals 53.32 degrees dew point. I think that's at our elevation, if my memory serves me correctly, at 1,100 feet, because elevation does impact the properties of air. Vapor pressure at this condition is 0.41 inches of mercury. Let's look at the design condition of a room. If we designed it to 75 degrees RH and we're experiencing a monsoon condition as described earlier, well, the room dew point is 55.13 and a vapor pressure of 0.438 degrees. If you're trying to control building humidity on a monsoon day, providing 55, 54 degree air off a cooling coil, that gives the building what is called a 1.81 degree dew point depression. You're only picking up 1.81 degrees dew point. Well, is that adequate to absorb the added moisture infiltrating your building from the outdoors at a 97, 78 degree design day? And this is where our challenge is. In Arizona, we were able to grandfather this into our designs because of our high summer dry bulb condition required so much airflow that we sort of slid under the limbo bar of tolerance for humidity control during the monsoon because we had to push so much air through a building. But as buildings are becoming more and more efficient, as sensible loads are becoming reduced, and consequently airflow is starting to fall, be aware that our humidity is still not being impacted. Our humidity levels remain the same. Our moisture level gains in buildings is remaining the same. So if we have insufficient dew point control or dew point depression of the supply air, we're going to start being challenged with humidity problems within a building. So let's look at a condition then. Let's look at a supply air condition of 55, 54 in a monsoon, supplying air at 53.32 degree dew point, a diffuser temperature of 55 degrees. We would assume, because that's the inner air condition at the diffuser, the room dew point at 75, 50% RH is 55 degrees. Your diffuser surface temperature is equal to room dew point. Condensation now occurs. You have those beads of liquid forming on your diffuser because its temperature is at dew point. Consequently, you have a humidity challenge in a space. So one of the things that we're advocating for, having been involved in a lot of chill beam projects and radiant cooling and heating projects as more recently, which is interesting, what we're looking at to properly control building humidity, suggesting maybe 48 degree dew point air off the cooling coil, meaning you'd be seeing 52, 50 degrees off the coil. If you provide that supply air condition off the coil and you're trying to condition a space with a 55 degree dew point, that gives you almost 6 or 7 degrees dew point depression. And that should give you adequate control of your humidity levels within your space. And I'll never forget working with Judy Peters of Daikin when we did the 100% outside air variable refrigerant article for ES Magazine. When Judy evaluated a decoupled 100% outside air variable refrigerant system providing depressed dew point supply air on the outside air at 48 degrees dew point, she said, "Dan, wow, this is interesting." She said, "The variable refrigerant air handlers become predominantly sensible cooling devices only." This is an interesting concept, and we'll explore further in future webinar Wednesdays. Well, what are our most challenging of conditions that we see for humidity control? That's in our hospital operating rooms. Operating rooms are being designed to 68, 75 degrees with relative humidity levels of 20 to 60% depending on the type of surgical procedures. Well, if you design a room or a surgery room to 68 degrees dry bulb, I'm hearing as low as 65, with 50% relative humidity, that's a room dew point of 48.7 degrees. Can you see the problem? If you're only providing 55, 54 degree air to an OR, that's 53.32 degrees dew point, and you're trying to control a space to 48 degree dew point, it'll never happen. In fact, you're adding moisture to the space. You're contributing to the humidity problem of a space. So a better solution is to look at drier air providing a minimum of 48-degree dew point to the space, if not lower, to pick up the moisture, the latent gain in the space given off by occupants and perhaps any other sources of liquid within the space itself. So with that being said, let's move on to how humidity impacts the risk of infection within the built environment. And I invite you to visit ASHRAE's position document on infectious aerosols and the wonderful resource that the Epidemic Task Force site offers in understanding humidity and why it is conducive to reducing the risk of infection and for enhancing human health. So we know that ASHRAE advocated through the Epidemic Task Force that airborne transmission of SARS-CoV-2 is significant and should be controlled. Consequently, it goes on to say that heating and ventilating systems can actually reduce the risk of infection, even of SARS-CoV-2, when properly laid out. The position document under paragraph 3.3 shows the relationship of temperature humidity and temperature and humidity. It goes on to say that HVAC systems are typically designed to control temperature and humidity, which can in turn influence transmissibility of infectious agents. Well, how? Well, we're going to explore that shortly. The weight of evidence, the position document goes on to say, the weight of evidence suggests that controlling RH reduces transmission of certain airborne infectious organisms, including influenza. The Masavi study of 2019, again an ASHRAE-sponsored study, came to this conclusion that scientific literature generally reflects the most unfavorable survival for microorganisms occurs when the room space humidity is between 40 to 60% RH. The Taylor and Tazi study of 2018 came to this conclusion that infectious aerosols emitted from a primary host shrink rapidly to become droplet nuclei, and these dormant infectious pathogens remain suspended in the air and are capable of traveling great distances. Well, the humidity level in a space determines the rate of evaporation for virally loaded droplets expressed by infected occupants. The Kudo study of 2019 goes on to state that mechanisms through which ambient RH below 40% impairs mucous membrane barriers and other steps in the immune system protection. That is to say, the drier the air, the more viscous the mucous membranes of our lungs becomes, and the less efficient our immune system becomes in allowing ingested contaminants and pathogens into our lungs from being evacuated from our lungs through mucus flow. The Gaffaw et al. 2009 study also writes that many viruses and bacteria are anhydrous resistant and actually have increased viability in low relative humidity conditions. I found that personally to be counterintuitive. I would have thought that higher humidity conditions would be conducive to bioagent generation, but that's not the case, certainly for viruses. They thrive in dry conditions and less so during this sweet spot range of 40 to 60% RH. ASHRAE's Epidemic Task Force also provides resources for how to lay out schools and universities to reduce the risk of infection, and it goes on to advocate proper temperature and humidity control to reduce the risk of infection. And in the school design guidelines, it references winter classroom conditions of being 72 degrees dry bulb, 40 to 50% RH, and in summer conditions at 75 degrees dry bulb, 50 to 60% RH. So look at that 40 to 50% relative humidity condition during our driest times of the year, fall, winter, and early spring. That's going to present a challenge. How do we reach those levels when it is so dry outside, when dew points can hit 20 degrees, 25 degrees? So anyway, something to be aware of. So how does humidity impact the risk of infection? Well, let's look at that. First of all, let's look at cold and flu season. When is cold and flu season? Late autumn, winter, and early spring, the driest times of the year, as we've demonstrated. Well, how does infection spread from an infected agent in a building to others? Well, we expiate. We express virally loaded droplets through talking, breathing, coughing, sneezing. Sizes of virally loaded droplets range from 1 micron up to 100 microns. The size of a SARS-CoV virus, close to an influenza virus, is about 0.125 to 0.15 microns. So they're very, very small. And depending on the violence of the expiratory event, breathing, talking, or coughing, discharge velocities of those droplets from the infected host can be anywhere from 2.2 miles per hour up to 44 miles per hour when somebody actually sneezes and projects virally loaded droplets up to 25 to 28 feet in a room. So the actual discharge plume evacuated from somebody also has different profiles depending on the violence of the event. Tidal breathing, you have laminar flow plumes of small droplets. Coughing or sneezing, you have bifurcated plumes coming off of an agent that can project large droplets far distances of 15, 20, up to 28 feet. So if we look at how those droplets are dispersed and their rate of evaporation, the rate of their evaporation, if it's high, will allow for desiccated viruses to be released into the atmosphere where they will free float in the space and become an infectious agent for other occupants. So you want to reduce the rate of evaporation within the space of those droplets so that they remain large, and due to the force of gravity will drop out of the air rapidly. So humidity does impact the release rate of viruses in a desiccated state into the air. By the way, I've read papers that suggested that SARS-CoV-2 can be viable 48 to 72 hours after the point of injection into a space. So they can stay in a room for a considerable amount of times. Well, the reason why humidity is an important factor is because droplets released by an infected agent, whether they're saliva droplets or mucus droplets, are predominantly water. And if you have a dry environment, those droplets will evaporate within 1 to 2 to 3 seconds, releasing desiccated aerosolized pathogens into the environment where they are more likely to free float and become an increased risk of infection to those in the environment that are beyond the social distancing guidelines. So the goal is, with a properly humidified space, is to reduce the evaporation rate of released droplets so they maintain their mass and they are able to drop out of the air more quickly where they cannot be breathed in by other people within the same space and putting them at risk of infection. So to give you an idea of why there is such a radical evaporation rate, I just ran the calculations of vapor pressure comparisons between a discharged plume of air from an infected agent, hopefully who's only at 98 degrees dry bulb at 100% RH, and look at the differential of vapor pressure, 1.8 to 0.35 in a room designed to 75 degrees dry bulb, 40% RH. You can see why those droplets evaporate all but instantaneously due to the force of radical vapor pressure differential. Now, this all makes sense when we're talking about people who are coughing and sneezing in a space, projecting large droplets far into a room. I had the opportunity to meet with Dr. Clifford Ho from Sandia Labs, who ran CFD modeling of airflow patterns in a space when infected agents are within a space. And he brought to my awareness that we need to take into account not necessarily just the coughing and sneezing. We need to look at simple tidal breathing of people who are infected with flu or any other type of virus or bacteria. Dr. Ho goes on to state that because the size of droplets that are emitted during tidal breathing are small, the exhaled aerosol plume can remain suspended for long periods. Dr. Ho goes on to write, thus, despite the lower viral load per exhalation event relative to coughs or sneezes, the persistence of the small aerosolized droplets and continuous nature of breathing and or talking can increase the potential for transmission, especially in closed spaces with low fresh air exchange. So I did the math with Dr. Ho's findings and ran the calculations. The average volume of air released by an adult is approximately half a liter with each breath. And the average adult person has roughly about 16 breaths per minute. So every minute, any adult within a space working away at a laptop or working on some papers or whatever at a desk will emit 8 liters of air, potentially if they are sick, with virally laden small droplets per minute. 8 liters of air per minute. So you can understand the magnitude of the impact of effective agents being in a space who are just working away, and the environment that is created that will enhance the risk of infection unless that condition is somehow impacted by humidity control or any of the other factors are solutions that ASHRAE's Epidemic Task Force recommends. So just to give you some sense of the scale and magnitude of how an infected agent might be putting other people at risk within a space. So another aspect for humidity is that if virally laden droplets stay in a droplet form, they maintain their water content, then if that droplet is ingested by another occupant within the space, that the water content of the droplet will more readily adhere to the wet surfaces of the mouth and nasal membranes and will not travel deep into the lungs. However, if that person ingests desiccated virus, free or broken free of the wetted surfaces of a droplet, that desiccated virus will not as readily be captured by the wet surfaces of the mouth and nose and will be drawn deep into the lungs, where they pose a graver health risk to the person who has breathed in those particles. So again, we want to make sure that the immune system is operating effectively if and when that does occur. We want to make sure that mucus flow from the lungs to out of the body is as efficient as possible so that any ingested pathogens may be more readily evacuated from the infected agent. So another reason why humidity reduces the risk of infection. The Sterling study, as sponsored by ASHRAE in 1986, determined that the optimum health range for relative humidity within the built environment is between 40 to 60% RH. The Stephen Welty study, done in 2013, demonstrated that 50% relative humidity indoors is a very good threshold to reduce the risk of infection within the environment. These studies go back to 1985, and there are a number of them that demonstrate relative humidity impacts the risk of infection. So the Stephen Welty paper advocates for humidity. Now be aware, because you control your humidity to a level between 40 to 60% RH that you're doing all you need to do to reduce the risk of infection. As ASHRAE's Epidemic Task Force advocated during the pandemic when it was in full flow, you always want to use a multi-layered approach to reducing the risk of infection, humidity being one of them, but you may want to increase your humidity during certainly our infectious time of year, our driest times of year, fall, winter, and spring. But also you might want to increase your air change rates. You might want to increase your outdoor air rate. You might want to apply UVC light technology. You may want to apply as well MER13 filtration. A bundled approach to reducing the risk of infection ASHRAE recommends, of which humidity is only one solution. So I wanted to bring to your attention, however, a new technology that has come out into the market, which we find very exciting, is there is now a plate and frame heat exchanger medium available where we can use energy recovery to drop water vapor that otherwise would be exhausted from a building back into the supply airstream to help reduce the risk of dehumidifying a space due to the exhaust air in a building that is necessary to maintain building pressurization. This technology is currently available in very small sizes of 30 CFM up to 10,000 CFM, and they can come in cross flow or what's the other name? I'm sorry, about counterflow, cross flow or counterflow applications. The new heat transfer medium uses a polymer membrane core that is 65% recovery efficient of latent energy, latent moisture. Well, what does that mean in a practical example? We know about enthalpy wheels and heat recovery for dehumidifying outdoor air during our summer monsoon conditions. Very effective at that. But if we reverse the process and apply it during our driest times of the year, you can have significant grains of moisture reintroduced back into your outside air stream and redelivered to your building if it's properly designed within a unit. And this particular sample shows a latent gain of 23.35 grains of moisture back into the supply airstream that otherwise would have been exhausted from a building without this technology. So that's, if you will, free rehumidification that is available in the industry using newer technology during our driest times of year, and will also reduce the latent load during our monsoon conditions, making HVAC systems more efficient. So that is it for today's session and presentation. We've covered a lot of ground today. We've looked at, we did a review of session 1 and what the properties and fundamental concerns were with HVAC systems. We looked at the nature of water, the states of water, the terms and definitions of those states. We looked at the physics of water vapor and water vapor flow from high humidity states to low humidity states. We evaluated ASHRAE's position document on infectious aerosols and its statements on building humidity to reduce the risk of infection. And we looked at how humidity how it practically behaves in reducing the risk of infection. So, any questions?
As of right now, there are no questions in the chat. So if you guys do have any questions, you can either unmute yourself and ask or pop them in the chat. All right, I don't see any messages coming in. If you do have any questions after this, always feel free to reach out to myself or to Dan or to your Varitec salesperson, and we can answer those questions for you. Dan, I'll let you wrap it up.
Well, thank you very much for joining us today. I hope you've got some good information from today's presentation, better understanding of the importance of humidity control and how to effectively provide humidity control for a building by properly designing and laying out heating and ventilating systems.
All right. Thank you so much, Dan. And thank you everybody for attending.
Thank you very much.